In this lesson, we'll review right-angle triangle trigonometry. If we look at all right-angle similar triangles with the same acute angle theta, it happens that the ratios between corresponding sides are always equal. So that means that ratios between any two sides of a right-angle triangle with a given acute angle theta depends only on this angle theta. And we assign special names for particular ratios. So let's recall how do we do that. If we have this triangle with the acute angle theta, then the side that you see across is called opposite to this particular angle. The side that is across right angle is called hypotenuse, and the side that is attached to the angle theta but not hypotenuse, it's called adjacent. You most likely remember the mnemonic SOHCAHTOA that helps us to remember the names of particular ratios. For example, if we compare opposite to the hypotenuse, that's ratio of sine with abbreviation SIN. So that's a name of a function, and this function takes an input. The input is theta. If we want to look at the ratio of adjacent over hypotenuse, we call such ratio cosine with abbreviation COS. Again, that's another name of a function, and the input for this function is theta. Another ratio is comparing opposite to adjacent. That's called tangent, abbreviation TAN. So that's a third function of theta. All these three functions you already learned before. Now in this course, we also introduce the other three functions, the reciprocals of the previous ones. So if sine theta is opposite to hypotenuse, then a ratio of hypotenuse over opposite, which is reciprocal of sine, is called cosecant with abbreviation CSC. If we take reciprocal of cosine, which is hypotenuse over adjacent, such function will be called secant with abbreviation SEC. So if you look at these two pairs, it goes kind of opposite way. Secant is a reciprocal of cosine, but cosecant is a reciprocal of sine. And the last ratio is the reciprocal of tangent, that means adjacent over opposite, and it's called cotangent with abbreviation COT. So those are basic definitions of 6 trigonometric functions, and we need to know them really well. Well, let's practice recognizing those ratios. Given the triangle, find the 6 trigonometric ratios of angle theta, and theta is here. Then find angle theta in degrees and in radians. So what kind of information we have in this triangle? It's a right angle triangle with the acute angle theta. We have one side of the triangle equal to 5 and the hypotenuse 8. For this particular theta, this side is called adjacent, and the 8 is our hypotenuse, and whatever we see across, it's opposite. Now, using the definition, let's state what's the value of each function. Sine of theta equals opposite over a hypotenuse. Well, in order to find out this ratio, we need the opposite. How do we find the opposite? Since this is right angle triangle, we can use Pythagorean equation. So let's call this side for a second x and solve Pythagorean equation. X squared plus 5 squared equals 8 squared, which gives us x squared equals 64 minus 25. Therefore, x by itself is a square root of 64 minus 25 is 39. So this value is really square root of 39. And now we are ready to give the values for each function. Sine of theta is root 39 over hypotenuse, which is 8. Cosine of theta is adjacent over hypotenuse, which is 5/8. Tangent of theta is opposite over adjacent, so it's root 39 over 5. And then the rest of the functions are really easy because it's enough to flip the values that we already have. So cosecant theta is reciprocal of sine, so it's 8 over root 39. And then the other two functions I will write over here. Secant of theta is reciprocal of cosine, so it's 8/5. And finally, cotangent of theta is a reciprocal of tangent, so it's 5/root 39. So we have the values of all 6 trigonometric functions of angle theta. Now we need to find this angle in degrees and in radians. Well, first in degrees. In order to find this angle, we can use one of those equations. I would suggest to use one of the first 3 because those functions are easily available on the calculator. So for example, if I use cosine theta equals 5/8, then theta by itself is actually inverse cosine of 5/8. Inverse cosine will be marked by cos to the minus 1, and you can recall this function from the calculator by using second or shift button. So second cosine gives you inverse cosine of the number 5/8. And then using calculator, theta equals, you check on your own, approximately 51.3 degrees. If you want this angle in radians, it's enough to change the mode on your calculator from degrees to radians and perform exactly the same calculation. And then theta would be approximately 0.89566. This is 5 places, that's definitely enough radians. If theta is an acute angle of a right triangle for which tangent is equal 3/4, find cosine, cotangent, and cosecant of theta. Well, how do we do that? We have a little hint here. Model the situation by drawing appropriate triangle. So let's draw a triangle that will have this ratio as a tangent. Okay, let this be the triangle. That's my right angle. This is theta. Therefore, tangent, it would be opposite over adjacent. And tangent theta should be 3/4. So if I will state that this side is 3 and this side is 4, I will get exactly tangent equals 3/4. Now using this model, we can figure out what's the hypotenuse. Let's call it x and use Pythagorean equation. X squared equals 3 squared plus 4 squared. But this is well known Pythagorean triple, 3, 4. We probably know that x is 5. If not, then you just calculate. It's very useful to know this Pythagorean triple because that saves you time. You don't have to really calculate anything you know of heart. The hypotenuse is 5, 3, 4, 5. Okay, since we know all the sides, we can just state what's cosine theta. Cosine is adjacent over hypotenuse, so it's 4/5. Cotangent theta. Cotangent is reciprocal of tangent, so it's adjacent over opposite, 4/3. And finally, cosecant theta. Cosecant is reciprocal of sine, so it's 1/sine theta. And we know that sine is 3/5, so 1/sine is 5/3. Next, we want to evaluate those trigonometric functions up to 4 decimal places. So how do we get secant of 3/5? First of all, notice that this is in radians, so you make sure that your calculator is in mode of radians. Secondly, you don't have the button of secant, so you actually need to rewrite this in terms of 1/cosine of 3/5. And that's how you enter to your calculator. Or you can calculate what's cosine 3/5 and then take reciprocal of the resulting number. So try on your own. The value of this function should be approximately negative 3.2361 up to 4 places. Now just remember that 1/cosine, it's not the same as inverse cosine. So those are 2 different functions. This is reciprocal and this is inverse function. So don't confuse the 2. Here we use reciprocal. The second question, cotangent. Again, we need to use tangent because there's no other button. So we need to translate this into 1 over tangent of 35 degrees 25 minutes. We already learned how to enter this type of angle by using the angle button and introducing the sign, degrees, and minutes. So again, let's do it on your own. You should end up with 1.4063. Obviously, those are approximate answers. So this question was in degree mode. If you've got any problem, check if your calculator is in degree mode. And the next question is again in radians. So switch your mode back to radians. And again, use reciprocal of sine of 1.5. This should be approximately 1.0025. Now we're going to review the special triangles that refer to angles such as 30, 45, 60. Those angles appear quite often, so it's a good idea to know off heart the values of basic trig functions on special angles. And these two special triangles will help us to memorize the relation between the sides. So the first special triangle is half of a square. So if the side of the square is x, both of these sides are x's. And then hypotenuse can be found by using Pythagorean equation. And you're welcome to check on that. When you use Pythagorean equation, the hypotenuse, let's call it d, will turn out to be x root 2. So whatever the side was times root 2. So the first special triangle takes care of the angle 45. The other special triangle is half of equilateral triangle. It takes care of angle 30 and 60 because in equilateral triangle all angles are equal and they are equal to 60. And this is half of 60, so it's 30. Sometimes this triangle is called golden triangle. It has a special place in geometry and in perception of beauty. So what are the relations between its sides? If half a side is called x, then the full side will be called 2x. And again, using Pythagorean equation, we can develop a formula for the height in respect to the half a side. The height in equilateral triangle is half a side times root 3. So in half of the square it's times root 2. In half of the equilateral triangle is times root 3. So it's easy to remember. Triangle 3, square 2. I can show you quickly this calculation, although I would prefer if you will do it on your own to check that this is the actual value. So if I call this hypotenuse d, d squared equals x squared plus x squared. Therefore, d by itself is square root of 2x squared, which is indeed x root 2. So from now on, we're not going to do these calculations anymore. We're going to refer to relations between sides of this particular triangle. Similarly, for half of equilateral triangle, if this height will be called h, then we have equation h squared plus x squared equals 2x squared. So h squared equals 4x squared minus 1x squared, it's 3x squared. And then h by itself, when you take square root, you have really x root 3. So yes, that's how it works. Okay, so now we can practice if we remember those relations. We have two triangles given. We need to find the exact values of all unknown sides. If a question calls for exact values, you don't use calculator. You need to find the exact value just by using arithmetic or algebra. So, since those angles are 45 degrees, therefore this really is half of the square, which means that the other side is also equal 5 root 3, and hypotenuse should be a side times root 2. So 5 root 3 times root 2 is actually 5 root 6. Therefore the hypotenuse is 5 root 6. Here we have 30 degrees and 60 degrees. 60 degrees tells us where's the base. That's the base. So if I want to extend this triangle to the full equilateral triangle, will look like this. And therefore this side is its height. Okay, but we remember that the ratio between a height and half a side is √3. Therefore half a side must be 5. As soon as I know that this is 5, the full side will be twice as much, so it's 10. So as you see, we didn't have to use any calculations, and knowing the relations between sides of special triangles, it's very easy to recover the unknown sides. Well, let's analyze a bit closer the values of the 6 trigonometric functions of the special angles 30, 45, and 60. First of all, let's change the degrees into radians, because we actually need to work in both, be fluent in both types of measurement. So 30 degrees is what part of 180? Well, 1/6, and 180 is pi radians. So the corresponding radian value should be pi 6. 45 is 1/4, so it's the same as pi quarters of a radian. 60 is 1/3, so it's pi thirds of a radian. And now looking at these special triangles with the unit sides, or unit half a side on this one, let's find out values of each trigonometric function. For example, if I look at the 30-degree angle, which corresponds to pi 6, that sine of this angle is opposite over hypotenuse, it's 1/2. And we plug it in the value here. Cosine of the same angle is √3/2. Tangent will be 1/√3. But notice that 1/√3, if you multiply by √3 in the top and in the bottom, let's do it on the side. 1/√3 times √3 here and √3 there to get rid of irrationality, we end up with √3/3. So it's either 1/√3 or √3/3. And now the other three functions, it's enough to just take reciprocals of the existing ones. So cosecant reciprocal of sine, so it's 2. Secant reciprocal of cosine, so it's 2/√3. Cotangent reciprocal of tangent, so it's just √3. Let's do the same for 45 degrees, which is in a special triangle coming from a square. This angle corresponds to pi quarters. So sine of that angle is 1/√2. Similarly as before, we could rationalize the denominator, and that would be equal to √2/2. So either like this or like that. Cosine of this angle is the same. So let's write down √2/2, the same as before. Tangent is just 1/1, so it's 1. And now reciprocals. So reciprocal of 1/√2 is √2, the same √2, and cotangent 1. And finally 60 degrees. Let's come back to our half of equilateral triangle. So 60 degrees corresponds to the angle pi thirds, and the sine will be √3/2. Cosine 1/2. So you see those values across are exactly the same. And tangent of 60 is √3/1. Now reciprocals of whatever we have, so it's 2/√3, which could be rationalized to 2√3/3. Reciprocal of 1/2 is 2, and reciprocal of √3 is 1/√3 or √3/3, which is the same. So we can always recover those values just by looking at special triangles. The next question asks us to find the exact values of the following expressions. So first, sine of 30. Sine of 30 is 1/2, and we need to square it. Plus cosine of 60. Cosine of 60 is also 1/2, and we need to square it. So it's 1/4 plus 1/4, it's 1/2 altogether. So this value is really 1/2. And the second example, now you can stop the video and try it on your own. Tangent of pi thirds is √3, so plug it in √3. Secant of pi 6 is 2/√3. Cotangent of pi quarter is 1. So overall, the root 3 reduces, and we end up with 2 minus 1, which is just 1. In the next question, we need to find the exact value of angle theta in radians if we know that theta is an acute angle. And we also know that sine of theta is root 3 over 2. Okay, sine of theta is root 3 over 2, therefore the theta by itself, it must be pi thirds. So we know that theta is pi thirds, just from the table. If we don't have this table close by, what we need to do is just sketch quickly the special triangle that involve root 3 and 2. So that must be half of equilateral triangle. This is 1, 2, root 3. Okay, so root 3 over 2 is sine of which angle? Well, it must be that angle. And now we recover, okay, this angle is pi thirds, or 60 degrees. Now let's look at the second question and assume that we don't have this table visible. So cosecant is the same as 1 over sine theta. Therefore, we know that sine theta by itself is 1/2. What is the angle? Again, the values 1 and 2 we can find by using half of equilateral triangle like before. So that's 1, 2, root 3. Therefore, 1 over 2 is sine of the small angle, which means either 30 degrees or pi 6. So we know that theta is pi 6. Here's a list of things to remember when solving trigonometry problems. First of all, make sure that you are in the proper mode, either degree or radians. So if your calculation doesn't make much sense, check the mode. When you calculate values of trig functions, use at least 4 digits. So for example, sine of 32 degrees 10 minutes should end up to be 0.5324 when you round to 4 digits. Please check it on your own. To find angles, always use inverse function. That means put the shift or second button before the function. And in case of angles, it's enough to round them to 1 decimal place. So for example, if we have equation cosine theta equals negative 0.35078, then theta by itself should be approximately 110.5 degrees, or if in radians, you may need to use more than 1 digits because radians are pretty sensitive. So that would be about 1.929, for example. So here I would say it's basically up to you how precise you want to have this angle. You can write 1.929, or you can also write about 1.9 radians. The other rule to remember is apply Pythagorean theorem only when you're working with right-angled triangles. Don't try to apply Pythagorean theorem for some other non-right-angled triangles. When you work with special angles like 30, 45, 60 or quadrantal angles, use exact answers. Some word problems will refer to an angle of elevation or depression, so it's good to remember that elevation always means from horizontal line and opens up, and the depression angle again always starts from horizontal level and opens down. As a matter of notation, in a triangle, opposite side carries the same name as the vertex. For example, if I have triangle PQR, then the opposite to P is called P, but it will use small letter. So side will be marked by small letter and vertices usually by capital letters. So this will be Q, that will be R. Also, the side that is opposite to smallest angle is shortest. So for example, this is the smallest angle, that's the shortest side. And the side that is opposite to the largest angle is the longest. To solve a triangle means to find all missing angles and sides. So whatever is not given, we need to find. And we have couple word problems to solve. The first one, the angle of depression to one side of a lake, measured from a balloon 2,500 feet above the lake, is 43 degrees. So here we have balloon. This angle is 43 degrees. It's measured from the horizontal line down till the edge of the lake. The angle of depression to the opposite side of the lake is 27. So again, starts from horizontal line, open it down till the terminal that points out to the edge of the lake. So this angle is 27. Find the width of the lake. So we need to find this distance. On the diagram is AB, but let's call it X. Notice that if I put two heights on this side and on that side, I can create two right-angle triangles. That means I can use right-angle trigonometry. And if I can find out this piece and that piece, then they all together give me the X. So let this piece be called A and that one B. So we know that X equals A plus B. And we need to focus on finding A and B. Using the first triangle, if I want to set up the trigonometric equation that involves angle 43, side A, and the given side 2500, then we have to use opposite over adjacent, which is tangent. So let's write down tangent 43 degrees equals 2500 over A. From here we can calculate A. A goes up and tangent goes down. So it's 2500 over tangent 43 degrees. Make sure that your calculator is in the gray mode. Plug it into the calculator. You should end up with 2680.9 feet. Similarly, using the second triangle, again this distance is 2500. So tangent of 27 degrees equals 2500 over B. Therefore, B, interchange the spots, B and tangent, they will replace each other. So B is 2500 over tan 27, which turned out to be 4906.5 feet. And finally, we need to add these two distances. So 2680.9 plus 4906.5, it's equal to 7587.4 feet. So that's the distance across the lake. And here we have another application problem. The angle of elevation to the top of the Egyptian pyramid of Cheops is 36.4. So this is the angle. And this angle is measured from a point 350 feet from the base of the pyramid. So distance from here to there is 350. The angle of elevation from the base of a face of the pyramid is 51.9. So if we measure the angle from this point, 51.9 is that angle. Find the height of the Cheops pyramid. So we need to find this distance. Let's call it h. We can see two right-angle triangles. That's right angle. The small one and the large one. And we can set up two equations involving the angle, the height, and possibly that distance. But in order to do that, we actually need to introduce one more variable to represent this piece from the center to the edge of the pyramid. So let's set up those equations. Using the small triangle, I can relate h to x, and that will give me tangent of the angle 51.9. Second equation we'll take by looking at the large triangle. So h over this overall distance, which is x plus 350 from here to there, equals tangent as well, but of the angle 36.4, both in degrees. Now we really have system of two equations and two variables, so it's possible to solve them. My suggestion is to solve each equation for h and then compare the values. So from the top equation, h equals, instead of tangent 51.9, we can plug it in the value up to 4 decimal places. So that turns out to be 1.2753 times x. The bottom one, similarly, h equals, tangent of 36.4 is 0.7373 times the denominator x plus 350. And since this is the same h, we can make them equal. Therefore, this will be equal to that. This is basically like substitution. Instead of this h, we're using this expression here. And then we have equation in one variable, 1.2753x equals, in the meantime we can multiply through the brackets, it's 0.7373x plus 258. Then we subtract the x's to the other side and we end up with 0.538x equals 258. And after dividing by 0.538x will be approximately 479.6 feet. So that's x. This is not the final answer yet, but now we can plug it into the first substitution equation and we end up with h equals 1.2753 times 479.6, which turns out to be 611.6 feet. So the pyramid is close to 612 feet high. And our last problem is actually a proof. We need to show that the area of a triangle with given two sides A and B and angle theta between them can be found by using formula 1/2 AB sine of the angle in between. So, how to prove it? Let's draw the height from the vertex B onto the side B. Let's call it h. And let's start with what we know about area of a triangle. Area of any triangle with base B and height h is 1/2 base times height. So we are okay to use B, but we should replace h in terms of A and theta. So h, A, and theta, they are related by this right angle triangle. What is the relation? Well, h over A is the same as sine of theta. So instead of h, we can write A sine theta. And now it's enough to replace this h in our formula, and we indeed have the 1/2 B A sine theta. Obviously, B and A could be written in the other order. So the proof is completed.